Okay, so the next revision video I'm recording before you commence your Unit 3 and 4 Maths Methods studies is a review of quadratic functions. Now obviously there's quite a lot to this, I'm going to skim over everything. If you need more specific instruction, please go back and have a look at, I'll link to some other videos, in particular probably I'll be uploading some Year 11 quadratics videos throughout Term 1. But in terms of what you can currently access if you're looking at this before the start of the year, which I hope you might be, what you can currently access is all of my Year 10 quadratics videos from last year. So there's a whole series of videos on quadratic algebra, factorizing, null factor law, completing the square, quadratic formula, all those sorts of things. And then there is a whole another series of videos on sketching parabolas. Okay, so transformations, turning point form, sketching it from turning point form or from polynomial form or whatever it might be. So there are lots and lots of videos dealing specifically with each of these skills if you need to brush up on those things. And can I please say, if these are not skills that you are strong at, you must brush up on these skills. Sketching a parabola, solving a quadratic equation, these are nuts and bolts things, in the same way that you know how to add without really thinking about it. If you're a Year 12 Methods student, you need to know how to do these things without really thinking about it. You're not going to be assessed explicitly on quadratics, but they will come up time and time again as part of other things. Okay. Alright, so the first thing let's have a quick recap on is sketching a quadratic function. So we might have our quadratic in this sort of expanded out general form or polynomial form, or we might have it in turning point form. We might also have it in a factorized form, in which case we'd know about the x-intercepts pretty quickly, and you can find halfway between the x-intercepts to find the x-coordinate of the turning point, let x equal 0 to find the y-intercept, etc, etc. So probably a third version there as well. If you've got it in, this is the least helpful form probably, if you've got it in this form, the only things you immediately know is if a, the coefficient of x squared, is a positive value, the graph has a minimum turning point. I call those happy parabolas, they're smiley. If a is a negative value, the graph has a maximum turning point and it's a sad value, a sad face shape, okay? So, negative a, sad, positive a, happy, easy. That's true of turning point form too. The a out the front, the dilation factor out the front, if it's positive, happy, if it's negative, sad. That's the first thing you want to think about. The first thing you want to identify is, right, this is a quadratic equation, so I'm going to draw a parabola. The second thing you want to identify is it a happy or a sad parabola? Then you want to think about what you know immediately, depending on the form that you've got. So if you've got this general form, the only feature that you definitively know by looking at the equation is the y-intercept will be that c value, because when you let x equal 0, you'll just get left with c. And then everything else you're going to need to work out. So x-intercepts are determined by solving this equation, which, if you can factorize it and use the null factor law, you're going to do that. If it won't factorize, you use quadratic formula to solve it. You can complete the square and then solve, but actually that's what the quadratic formula is. The quadratic formula is a shortcut for completing the square. So I never use completing the square to solve an equation. It drives me mad when textbooks spend a lot of time, asking you to solve this equation by completing the square. You just wouldn't. That's what the quadratic formula is. The reason to complete the square is to be able to convert to turning point form, to convert equations of circles into a helpful form, a couple of other sorts of things, but it's not about solving. So factorize and null factor law, or failing that, use quadratic formula. Axis of symmetry, once you've got your x-intercepts, the axis of symmetry is halfway between your x-intercepts. So halfway, average your x-intercepts to get the x value, sub that in to get the y value, or you can use this formula, negative b on 2a, which gives you the axis of symmetry as well. Turning point form, again, happy or sad first. This is helpful because immediately you know the turning point is at hk because the graph has been dilated by a factor of a from the x-axis, translated to the right by h, assuming that h is a positive number, and translated up by k, assuming that k is a positive number. So the turning point therefore is at hk, and then you find the x-intercepts by solving this equation. And the nice thing about this equation is a times x minus h all squared plus k can be solved, equals 0 can be solved simply by rearranging. Do not expand out that perfect square. take away k, divide by a, take the square root, add h. Okay, you do not need any quadratic skills. You should be able to give that to a year 7 student who knows nothing about quadratics but who knows about equation solving, and they should be able to solve that, because all you're doing is just do the same thing to both sides until you get x on its own. Do not expand. And the y-intercept is found by substituting x equals 0. Note, the y-intercept is not the number on the end. It is here because when you let x equal 0, you just get left with c. But here, when you let x equal 0, you don't get left with k. Okay, so that's another common mistake. If we want to get from general form to turning point form, we can complete the square. Okay, so if you'd prefer to sketch it this way, you can complete the square first and then do this. You also might need to complete the square if, when you try to solve this, it doesn't have any x-intercepts. Then you're going to want to complete the square so that you can work out what the turning point is. Or you could use negative a on 2a to find the turning point. Okay, let's sketch a couple of graphs. As I said, plenty more details in other videos you can go and look at. Sketch graphs of each of the following. Okay, so the first one is in this sort of polynomial form. The immediate things I'm noticing without doing any calculation, it's positive x squared, and so therefore it's a happy shaped parabola, and the y-intercept is going to be at negative 8. Those are the two things I can see straight away. So the y-intercept will be at 0, negative 8. The x-intercepts, I'm going to try and find those, so letting y equal 0, same for all functions. If you want to know the x-intercept, you want to know what is x when y is equal to 0. I'm going to try and factorize that, which it will factorize. Factors of negative 8 that add up to negative 2, x minus 4x plus 2. Null factor law tells me that x minus 4 equals 0, so x equals 4, or x plus 2 equals 0, so x equals negative 2. Okay, so there's my two x-intercepts, 4, 0, and negative 2, 0. The turning point is going to be halfway between the x-intercepts, so averaging the x-intercepts. 4 plus negative 2 over 2. 4 plus negative 2 is 2 over 2. Okay, so the x value of the turning point is 1. And then I need the y value, obviously. But here I've got an equation that connects x and y. So I sub x equals 1 into my equation to work out what y has to equal. So 1 squared minus 2 times 1 minus 8. So 1 minus 2 minus 8. That's 1 minus 10, so negative 9. So the turning point is at 1, negative 9. We've got all the information we need to sketch the graph. So find your information before you draw your axes. Okay, I've got a smaller negative x-intercept and a bigger positive one. So I want my y-axis to be sort of to the left, and I've got mostly negative y values. So thinking about where you want your axes to go. Going to make that negative 2, which would make that positive 2, and that positive 4. So again, you want consistent scale along your x-axis. So don't make this negative 2 and then this positive 4. The scale won't be right, and then you'll have trouble when you're then trying to get your graph to actually fit the right y-intercept. You'll end up with a parabola that you're going to try and bend so that it fits your poorly scaled, x-intercept. So good scale will help you with graph shape as well. And there'll always be a mark associated with shape, or part of the mark allocation will be associated with shape. Okay, so my turning point has an x value at positive 1. I'm just going to mark it down here, so that's going to be 1, negative 9 down there. And again, I want consistency in my scale, so I don't want my y-intercept of negative 8 to be up here if this is negative 9 down here. Okay, so you do need to sort of think a bit. I'm not going to mark it in perfectly. I'm just going to think in my head, right, I want it to be sort of close, maybe somewhere down here. If I don't hit precisely there, it doesn't matter. I'll label it later. And then it helps to mark a symmetric point. So it means if I want to hit here, then I also want to hit somewhere here. Again, that'll help you with your shape, because you want your parabola to be symmetric. If it's not symmetric, you're not demonstrating that you're understanding what a quadratic function looks like. Okay, so that is the point 4, 0, labeling everything with coordinates. Important habit to develop. VCA always ask for coordinates. And there's my graph. Alright, part B, the graph is in turning point form. So the 2, it's positive, so it means I've got a happy shape, dilation by 2 from the x-axis. That doesn't really affect how I draw the graph. The key things are that the graph has gone to the right by 1 and down by 3. Which tells me that my turning point is going to be at 1, negative 3. my y-intercept, I'm going to let x equal 0. So 2 times 0 minus 1, so it's negative 1 squared minus 3. Negative 1 squared is positive 1. 1 times 2 is just 2. So my y-intercept is at negative 1, so that's going to be 0, negative 1. And my x-intercepts. The other thing to think about too, particularly if you've got the graph in turning point form, not all parabolas will have x-intercepts. So don't launch into finding them if you don't know that if you know that there won't be any. So there are two things that are important for that. Here we've got our turning point is somewhere below the x-axis, and we know the shape is happy. So if it turns below the x-axis with a happy shape, it's going to have to cross the x-axis. But if it was negative out here, then this graph wouldn't cross the x-axis at all, and I wouldn't bother trying to find the x-intercepts because there won't be any. I'll just find myself halfway through trying to square root a negative and then realizing, oh, I should have thought about it at the beginning and I know there wasn't any. But there is in this instance, so we're going to let y equal 0. As we talked about earlier, we're not going to expand that perfect square because this turning point form is great because it can be solved without any quadratic specific skills. We're simply going to add 3 to both sides, divide both sides by 2, take the square root, bearing in mind that when we take the square root we get plus minus square root, that's where we're going to get our 2 x-intercepts. And so x adding 1 is going to be 1 plus or minus the square root of 3 on 2. Now if you want, you can rationalise the denominator there, multiplying top and bottom by root 2, which would give you root 6 on 2, but it's not necessary to do that. In methods you don't need to give rational denominators, you can leave it as root 3 on 2 or root 3 on root 2, that's fine. Now, it doesn't matter that we don't know how big that number is. I mean, you could get a rough estimate, but it doesn't matter. Okay, so you just need to be, you know, if you plot everything else out right, then they'll fall in roughly the right place. It doesn't really matter how big that is. So my turning point's at 1, negative 3. My y-intercept is at negative 1. Oops. Not the straightest x-axis, sorry, let's try that again. Okay, what did I say? 1, negative 3. Let's make that there. So if that's negative 3, then negative 1 is going to have to be somewhere about there. That's where I want my y-intercept to be. So a symmetric point is going to have to go through somewhere about there, which means the x-intercepts are sort of going to be around there and there, just thinking about the shape. Okay, it's hard to get them in the wrong place if you take a bit of care in terms of, you know, plotting out everything else. Oh, I missed that y-intercept. Let's get it right. Missed it the other way. That's why you need a pencil. It's a bad shape. Sorry. It's easier to draw them in 2 halves, the parabola. So stop at the turning point, or particularly for me with the electronic pen because I can't. It's easier to rub out the whole stroke. So it's easier to split it so I can rub it out in separate sections if I need to. Okay, so that's my y-intercept at 0, negative 1. This x-intercept is 1 plus the square root of 3 on 2, 0. And this x-intercept is 1 minus the square root of 3 on 2, 0. I mean, you can think through the size of that number. You know, 3 on 2 is 1.5. The square root of 1.5, well, the square root of 1 is 1 and the square root of 4 is 2. So the square root of 1.5 is going to be pretty close to 1. Bigger than 1, but close to 1. So 1 plus a number a bit bigger than 1 is a number a bit bigger than 2. 1 minus a number a bit bigger than 1 is a number just a bit less than 0. Okay. So that should marry with what you're seeing. Okay, completing the square. There's a link there to a video specifically on completing the square. That's a bit older video, that one there. I might link in the description box to a more recent video, the one I did with my Year 10s last year, but there's a couple of videos already up there in the channel on completing the square with some more detail. Okay, so by first completing the square, determine an appropriate sequence of transformations that transforms y equals x squared to y equals x squared minus 4x minus 6. Okay, so turning point form allows us to see those transformations, so we want to complete the square. So we're going to start with x squared minus 4x minus 6. Now, completing the square, we want to create that perfect square using the first 2 terms. I'm not going to worry about the negative 6, we'll just pop that over there. So we want to create the perfect square here. Okay, so properties of perfect squares when they're expanded is if you take the coefficient of x and you halve it and square it, that will give you the number that goes on the end, the constant term. So half of -4 is -2. -2 squared is +4. So we need +4 here so that that is a perfect square. I can't just add in 4 to the equation because I feel like it. Now I've made a different equation, so I take away 4 as well. So I haven't actually changed the value of the total equation, but what that allows me to do is take these first three terms and factorize them as the perfect square. So it is x minus 2 all squared. Okay, this, if you take that number and halve it, that will tell you what goes in the perfect square. I prefer to think about that. Okay, yes, it's the square root of that, but the square root of +4 could be positive or -2. Sorry. If you think about it as being half of this, that will tell you about the sign that you need. And then outside of the perfect square, we've got -4 and -6, so that's -10. Okay, so we're looking at how do we get from y equals x squared, so the basic parabola, to y equals x minus 2 all squared minus 10. So that -2 in the bracket translates, now when you're listing transformations, we'll talk more about transformations down the track, but you always need to use the word translation or dilation or reflection. So you can't talk about stretching or mirroring or flipping or moving or shifting. So list the sequence of transformations. So it is translation right by 2 units and also translation down by 10 units. So it's just the two transformations. No dilation or reflection, that would be sitting at the front here. Alright, example 3, sketch y equals 2x squared minus 4x plus 7 by first expressing in turning point form. Okay, so we don't have to, but the instruction, you know, if the question is just this, you can do it in different ways. You don't have to convert to turning point form, but in this instance, it's asking us to do it this way. And actually, when we see what happens, it ultimately is the most efficient way. So we want to express in turning point form. Now, the key thing is to get in turning point form, apologies for that, we want to complete the square. And the key thing is that you cannot complete the square for a non-monic quadratic. Okay, so if there is anything other than 1x squared, even if it's -x squared, so this is 2x squared, so you must factor that out. Even if it means making fractions, you just have to do it. So we've got x squared minus 2x plus 7 on 2. Some people just leave the 7 and worry about it later. Don't put it in the bracket. It's up to you. I prefer to just take the factor of 2 out at the beginning and worry about it later. Now, the mistake you'll make is somewhere along the way here you'll forget about your factor of 2. So whether you actually do it, whether you just imagine it, I want you to really consciously think about, you've got this big 2 out the front and these red brackets, and until you consciously multiply everything by 2 again, it's got to stay there, okay? Alright, let's focus on completing the square inside the bracket. X squared minus 2x, half of -2 is -1, and squaring that is +1, so that makes the perfect square. I'm going to take away 1 as well, and then I've still got this plus 7 on 2 over here. These first three terms, they are my perfect square, okay, and it's half of -2, so it's x minus 1 all squared. And then outside the bracket we've got -1 plus 7 on 2. -1 is -2 on 2, so -2 on 2 plus 7 on 2 is plus 5 on 2. Okay. Now this line that I've just finished here, this would be the line where you would have forgotten to put this bracket in, because you'll have got excited about writing a bracket for the perfect square and you'll have forgot the fact that the whole thing's multiplied by 2. And at this point you'll have ended up with the line that says this, but that's not the correct answer, because you've now got to multiply the 2 back in. So it's 2 times the perfect square, but also 2 times the 5 on 2. And because 2 is something that you took out as a common factor, you should find that it always cancels down with that fraction at the end, which might not always be a fraction, but if it is a fraction, it'll always cancel out with the denominator. So we're going to have, 2 times x minus 1 all squared plus 2 times 5 on 2, don't write it as 10 on 2, cancel the 2 with the denominator, the 2 in the denominator, so it's just plus 5. So there it is in turning point form. We want to sketch, so we've got +2 here, so it's a happy parabola, a bit of a dilation. We've gone to the right by 1 and up by 5, so the turning point is at 1, 5. Okay, So if we've got a happy parabola with a turning point at 1, 5, i.e. a turning point above the x-axis, we're not going to be crossing the x-axis. So we've got no x-intercepts. The y-intercept, I'm going to go back to this form of the equation because it's easier to calculate it there than to have to actually do the calculation here. So it's easier to let x equal 0 up here and find that we get 7 rather than in this version. So once you've got the equation in two forms, be flexible about where you get your information from. Okay. So our y-intercept is at 7, our turning point is at 1, 5. 1, 5 and 7 is going to be a bit above that. Again, a bit of consistency about your scale. You know, if this is 5 here, don't put 7 all the way up here, okay? Because then you're saying that distance is 5 and that distance is 2. So just think a bit about it. It doesn't need to be perfect, but I just want to be, you know, a little bit above it. And then for symmetry, same kind of level point somewhere over here. Y-axis, x-axis, making sure all my points are labelled. So any intercepts and turning point. Minimum information on the parabola, turning point plus one other point, but you must have all axis intercepts marked. Okay, and there's my graph. Completing the square using your CAS is menu 3, 5. That's something I use quite frequently. I find it's often something that students are unaware of. So if I want to do this example 3, complete the square for 2x squared minus 4x plus 7, comma x, you always need comma x for completing the square, and there it is there, so we did it correctly. I use it quite often if you want to find a turning point for a quadratic. You've already got the function defined. You don't want to muck around with the graph, just complete the square. It's also easier to complete the square than solve derivative equal to 0, etc, etc. So I use completing the square quite a bit with my CAS, and as I said, I find it's something students don't seem to be aware of that their CAS can do, or they just don't think to get their CAS to do it. But if you've got your CAS, by all means, you shouldn't ever be completing the square by hand. There's an example down here in the screenshot of where completing the square is useful when you've got an equation of a circle. It might obviously also, if you've got some, you know, a literal equation with some non-numeric coefficients, it might be easier to get your CAS to do it than to do it by hand, although I'm not saying that's not possible to do by hand, but get your CAS to help where you can. Okay, solving some equations. We've done a bit of that as part of the graph sketching, but just a quick review. So in your head, you really want to be able to think through a process, and I actually have a flowchart that you'll see if you look at some of my Year 10 videos. The first thing you want to think about is, can you rearrange it? So like the equations in turning point form, can I just rearrange it to get x on its own? If you can't, you then want to try and factorize and use Null Factor Law. Okay. If it won't factorize, you then want to use the Quadratic Formula. As I said, you can complete the square instead of using Quadratic Formula, but the Quadratic Formula is completing the square. It's a shortcut for completing the square. So I don't ever complete the square when I'm to solve a quadratic. So those are the things you want to think about. Can I solve it by rearranging? Yes, do it. No, move on to the next option. Can I factorize this? Make one side 0 and then can I factorize what I've got? Bearing in mind the first step of factorization is take out any common factors, or if they're in an equation, if they're numeric common factors, you can divide both sides by that common factor. And then if I can't factorize, then I'm going to go to the quadratic formula. So try and be, again, systematic. We talked about that if you've watched the linear equations one. You know, yes, there's lots of different ways you can do it, but try and have a process. I deal with fractions first, then I deal with brackets, then I collect like terms, then I solve from there. In this case, I rearrange if I can, then I use factorize if I can, and failing that, I use quadratic formula. Okay, so we did a bit of rearranging in the graph sketching. Here, if we can't rearrange, then we're going to use the Null Factor Law, which requires factorization. So these equations can't be rearranged because you've got x in more than one term and they're not like terms. So immediately, step 1 is not an option. So we're going to try and factorize. Before you try and factorize, you want to make sure you've got the null part of the Null Factor Law. So one side has to equal 0, then you try and factorize the other side. First thing you're looking for with factorization is, are there any common factors? And in this case, yes, there are. 2x is a common factor, and we're going to be left with, sorry, that'll be 3 minus x. Now, we need to be a bit careful here. We can actually get rid of the 2 because we can divide both sides of the equation by 2. So we could, if we want, just write this as x times 3 minus x equals 0. But you can't divide both sides by x, and that's the mistake that students often try to make. If you divide by x, you've made the assumption that x can't equal 0, and in fact in this equation x equals 0 is one of the solutions, so you're losing a solution. I wouldn't bother in this case dividing away the 2. It's easy enough to go straight to my null factor law here. You can think about this in 2 different ways. Either you're thinking about 2x equals 0 or 3 minus x equals 0. This gives x equals 0, or this, and this gives x equals 3. Or at this point, you can think about, actually, I've got 3 things multiplying together here. 2 could equal 0, which is ludicrous, or x could equal 0, or 3 minus x could equal 0. Okay, the whole idea is things multiplying together to equal 0. Each one or other or all of those things has to be equal to 0. You don't need to write out this step. Yes, you can go straight to writing down x equals 3, but again, being really mindful about what it is that you're actually doing. The null factor law comes up in all sorts of other areas, and if you don't understand what it is and what it's doing, you don't think to use it in those other areas. For example, down the track, I might give you an equation like e to the x times sine of x equals 0. And the idea that you have 2 things multiplying together to equal 0, so either this thing must equal 0, or this thing must equal 0, allows you to go on and solve that equation. Okay, so it's not just for quadratics, it's not just for polynomials. It's a really important idea that if you have things multiplying together to be equal to 0, that allows you to use the null factor law. Okay, part B, we've already got the null part. We want to focus on the factorizing part so we can then use our null factor law. So this is a non-monic quadratic, so a number other than 1 here. So we had an example when we were sketching the graphs. I think it was x squared minus 2x minus 4, I think we solved. We factorized. And where that's a simple or monic quadratic, 1x squared, you can factorize in one line, and you should factorize in one line. Factors of this, that add up, sorry, it wasn't minus 4, it was minus 8. Factors of this that add up to this, factors of negative 8 that add up to negative 2. Okay, so you have x's in both brackets, that's how you get the x squared when you expand. 2 things that multiply together to give negative 8 that add up to give negative 2 are negative 4 and positive 2. Okay, and you're done. If, however, it's not 1x squared, you need to do a bit more work. Now, you can, some people talk about, oh, I use the cross method. Again, the cross method is just a trial and error method that you set up, you write out in a particular way. That people have called the cross method. It is just trial and error. And for some equations, and this is an example of that, trial and error, many of you will be able to factorize this essentially using trial and error, and you'll be able to say, well, okay, and it's because these numbers are both prime, okay? So there's going to have to be a 2x in one bracket and an x in the other bracket, and the numbers are going to have to be 1 and 3, and 1 has to be negative. How do I get it to work? You know, that would give me minus 6x plus 1x, which is minus 5x. So that's it factorized. Some of you will be better than that at that than others. If you're not comfortable with that, or you don't find that very efficient, I tend to teach this. I don't know. It's essentially it results in factorization by grouping. I tend to teach this process because it works for all non-monic quadratics, and particularly too where you've got, if these numbers both have lots of factors, if this was 12 and this was 36 or whatever, then the trial and error process you could be there quite a long time. So this process, we're going to do the coefficient of x squared multiplied by the constant term, so that is 2 times negative 3, which is negative 6. And we're then looking for factors of negative 6 that add up to negative 5, so they are going to be negative 6 and positive 1. Then what we do is we're going to break up this middle term so we can factorize by grouping. So we're going to keep the 2x squared at the beginning, and we're going to keep the minus 3 at the end. And we're now going to use these 2 numbers that we've got here, the negative 6 and the positive 1, to break up this term. So this is going to become minus 6x plus 1x, which is just plus x, obviously. So that then I'm going to split my equation in half and factorize by grouping. So I'm going to just look at the first 2 terms and factorize. Look for common factors. Common factors there are 2x, which leaves me with x minus 3. And then I look at the second 2 terms and look for common factors. Now there's no common factors there. Well, there is. The only common factor is 1. But it is helpful to this process to actually write it out with the 1 as the common factor. Because now what we're identifying is this bracket, x minus 3, that's the common factor. So we take that out, and when we take that out, we're going to be left with 2x plus 1. Okay, so now we've factorised and it equals 0, so we can use our null factor law. X minus 3 equals 0, which means x equals 3, or 2x plus 1 equals 0, which means 2x equals negative 1. So x equals negative a half. Please never write the word and here. We'll review set notation coming up, but and is the intersection. There is no intersection between x equals 3 and x equals negative a half. If you must write a word, it should be or, which is the union. Okay, but just don't write anything. Put a comma or don't write anything. Okay. If we can't factorize, we're going to use the quadratic formula. So here is our quadratic formula here. That is a formula that you should know, okay? Negative b plus minus the square root of b squared minus 4ac all on 2a. That comes from taking this equation and solving it by completing the square. If you watch, I'm not sure whether it will be this video, but I'll link a video on the quadratic formula where you'll see me actually work through that process to arrive at the quadratic formula. Again, I've got plenty of videos on quadratic formula. There's a year 10 one from last year. I will have a year 11 one going up as I go through that during term 1 with my year 11 class this year. So by all means go and have a more detailed look at those. So when factorization is impossible, we're going to use the quadratic formula. So part A, if we're solving this equation, so again, it's not going to say solve using the quadratic formula. You're going to go through that process. Can I rearrange it? No, because there's more than one term involving x and they're not like terms. Can I factorize it? Well, it's currently a non-monic because it's negative x squared. So first thing I'm going to do is rewrite it so I've got a positive x squared term. It makes everything easier. And you can think about that in two ways. We can think about sort of adding everything so that it ends up on the right hand side. We can think about multiplying everything by negative 1, okay, however you want to do it. But we're essentially going to end up with positive x squared, positive x, and negative 3 being equal to 0, however you think about it. If we tried to factorize it, factors of negative 3 that add up to positive 1, the factors of negative 3 are negative 3 and positive 1, or positive 3 and negative 1, and however you look at it, they don't add up to positive 1, so we're going to have to use quadratic formula, or complete the square. So x equals, so in this case, a is 1, b is 1, and c is negative 3. Okay, so x is going to be negative b, which is negative 1, plus or minus the square root of b squared, 1 squared is 1, minus 4 times a, which is 1, and times c, which is negative 3, all over 2a, 2 times 1. So we've got negative 1 plus or minus the square root of, that's 1 plus 12 over 2, and so negative 1 plus or minus the square root of 13 over 2. Now you must make sure this is in simplest form. In this case it is, but there's two things you want to look at. The first is my surd in simplest form? So we're looking for square numbers that go into 13. 13's prime, so there aren't any. If then once I have simplified my surd, so let's say you might have a completely different equation where you've ended up with square root of, and you've simplified your surd, and you've now got 2 root 7 over 4. Okay, and so then you're going to look at simplifying the fraction, and that is about looking for common factors. And again, it's not about just cancelling down that and that. You need a common factor in the whole numerator, so you want to be able to factor out 2 as a common factor, so that'll be leaving with negative 1 plus or minus root 7 over 4, and then that will cancel down, so we're going to have negative 1 plus or minus root 7 over 2. In this instance, the surd doesn't simplify, and therefore there are no common factors in the numerator for the fraction to simplify, so we're all done. You don't need to write them out as two separate solutions, x equals negative 1 plus root 13 on 2 and x equals negative 1 minus root 13 over 2. Obviously if you're labelling a graph you'd write them out separately, but otherwise it's fine to just leave the plus minus. Okay, again here we're looking for, now the other time you might use quadratic formula is if the numbers are a bit ugly. So here the first thing I'm looking for is the numbers are all quite big. I'm looking, is 3 a common factor that I could divide the whole equation by 3, but it doesn't go into 25, so I'm stuck with it. If I'm going to try and factorize, I'm looking for factors of negative 75 that add up to 12. I don't think they are. 75 is sort of big. I'm not that comfortable with the factors of 75. I might have missed something. I don't really know. If I get a bit stuck in that way, then I'll probably go to quadratic formula too. In this instance, there aren't factors of 75 that add up to 12, so we're all good. even negative 75 that up to 12. No. Okay, let's launch to our quadratic formula then. We can't simplify it at all, so if you could divide out a common factor, do that. Make your numbers as small as they can be, but there's no common factor here. So A is 3, B is 12, and C is 25. So quadratic formula tells me that x is going to be equal to, also it's x equals the quadratic formula. It's the solutions to the equation. Okay. X equals negative b, so negative 12, plus or minus the square root of b squared, which is 144, minus 4 times 3 times 25, all over 2a, so 2 times 3. Let's tidy that up. 144 minus, now again, 4 times 3 is 12, and then 12 times 25, now that's a bit complicated. Be flexible about your number work. 4 times 25 is 100. 100 times 3 is 300. Okay, so again, flexibility is really important. Now, this is a problem in here, because 144 minus 300 is going to be negative. You can't square root a negative, and so therefore, this equation has no solutions. But we don't know that until we try to solve it. It can be a good habit to, this bit under here we call the discriminant. Talk about the discriminant a bit more over the page, I think. Discriminant, which is the b squared minus 4ac. The discriminant doesn't involve the square root. The discriminant is just b squared minus 4ac. And if the discriminant's negative, there won't be any solutions, as we can see here, because we can't square root a negative. So it can be a good habit to find the discriminant first. Then if it's negative, you don't go any further. If it's positive, you can straight away kind of go to this point, because you straight away know the discriminant's 13. So it doesn't slow you down at all. Anyway, this one doesn't have any solutions. Okay, solving a quadratic inequality. So when solving a quadratic inequality, in fact, any non-linear inequality, you must consider a graph. Okay. Yes, it's connected to solving the equivalent equation, but you won't know whether your answer is between the solutions you've got or outside the solutions you've got, or whatever it is, unless you're looking at a graph. Okay, so you must consider a graph. It doesn't matter how big I make the font of this sentence. It doesn't matter how many, pink boxes and highlighters I use. I find that you will ignore it. Everyone thinks they're going to be the first student ever who can solve a quadratic inequality without the need to think about a graph, but I'm here to tell you that that's not possible. So, for example, if we're trying to solve this inequality, this quadratic inequality, x squared plus x minus 6 is less than 0, we want to look at the graph of y equals x squared plus x minus 6, and then we're looking at where is y less than 0, okay? Because if this is y, then it becomes y. Where is y less than 0? Once you've drawn the graph. So you draw the graph. It doesn't need to be a perfectly precise graph. You really just need the x-intercepts and whether it's happy or sad in shape. This factorizes. The x-intercepts are at 2 and negative 3. It's a happy parabola, so this is what it looks like. We want to know, so this is y equals x squared plus x minus 6. We want to know where x squared plus x minus 6 is less than 0, so where y is less than 0, and that is clearly down here. Okay, so in terms of the x values where that happens, it is between this x value and this x value. So between, when x is between 2 and 3, the y values will be negative, and hence the quadratic is less than 0. Okay, it has to be less than 0, so we don't want to include. Okay, if this was less than or equal to 0, the original question, then negative 3 less than or equal to x less than or equal to 2 would be the answer. Okay, so as I said, it doesn't need to be a detailed graph. It's really about where are the x-intercepts, which way up does it go, where is it below the x-axis. Notation, we'll review the set notation down the track. You can just write it as the inequality for now. You can write it as an interval. Technically speaking, as a set, you would write it in that way. Yeah. Also, once you've drawn the graph, you then also have the answer to the question. If it was where is x bigger than or equal to 0, you can see it would be bigger than or equal to 0 either outside of those two values. So when x is less than or equal to negative 3, or when x is bigger than or equal to positive 2. Okay. Alright, let's do our own. Let's solve this quadratic inequality. So we want to consider the graph of, we want to sketch, sorry, let's try that again. We want to sketch y equals 3x minus 6x squared, then consider where y is less than or equal to 0, because we've essentially let that be y. Okay? So that is where the graph is on or under the x-axis. Okay, so factorising this, 3x is a common factor, leaves us with 1 minus 2x. So x-intercepts are at 0 and positive half. Okay. It is a sad parabola, the negative x squared term. So it looks something like that. That's half and that's 0. We want to know where the y values are less than or equal to 0. So the y values are equal to 0 at those 2 points and less than 0 down here. So when x is bigger than or equal to a half, or when it is less than or equal to 0. Okay. So x less than or equal to 0, or x bigger than or equal to a half. Perfectly fine with that notation. We'll review the set notation later. As an interval, it would be x is an element of negative infinity to 0, union half to infinity. Again, make sure you write or if you're going to write a word, don't write and. Discriminant. So we talked about the discriminant as being the bit under the square root of the quadratic formula, the b squared minus 4ac. If that value is positive, then when you take the square root of a positive number, you get plus minus, so we get 2 solutions. If that value is negative, the square root of 0 is 0, and we lose that whole bit of the equation, and the equation has just one solution, and that solution is x equals negative b over 2a. And if the discriminant is negative, you can't square root a negative, and the whole thing goes to pieces, and there are no solutions. Should say no real solutions. Yes, there is such a thing as non-real numbers. If you are studying specialist maths, you will learn about those. Okay, so we don't tend to use the discriminant. We don't tend to get a question that says, here's a quadratic, tell me how many x-intercepts it will have, or how many solutions this quadratic equation will have. This comes up in other contexts, and this is one of those sort of examples. So for which values of m does the quadratic equation have one solution for x or 2 solutions for x? Okay, so one solution for x will be when the discriminant is equal to 0, and 2 solutions will be when the discriminant is positive. So the first thing we want to do to answer both of these questions is to find the discriminant. So the discriminant is going to be b squared, in this case b is m, so it's going to be m squared minus 4 times a, which is 2, and c, which is 5. So discriminant is m squared minus 40. Okay, so for part A, we want to know where the discriminant is equal to 0. So where m squared minus 40 equals 0, m squared equals 40, m is the positive or negative square root of 40, which is not a third in simplest form. Square number 4 goes into that. So that is the square root of 4 times 10. The square root of 4 is 2, so it is 2 root 10. So for which values of m does the quadratic equation have one solution for x? Okay, so if m was either of these two values, if that coefficient, so if we had the quadratic equation 2x squared plus 2 root 10x plus 5 equals 0, that would have only one solution. Similarly, if it was minus 2 root 10x plus 5, that would have only one solution. Okay, so m equals plus minus 2 root 10 is the answer to part A. For part B, we need the discriminant to be positive, which means we need m squared minus 40 to be positive. That is a quadratic inequality. So we want to think about the graph of this. Okay, so the discriminant is equal to m squared minus 40 is just a parabola shifted down by 40. So if these axes are now m and discriminant, okay, we've already worked out when the discriminant equals 0. We did that in part A, so this is 2 root 10 and minus 2 root 10. So we want the discriminant to be positive for 2 solutions, which means that we're looking at above the x-axis where the discriminant is positive. And so that will be not at negative 2 root 10, but any x value less than negative 2 root 10 will give a positive discriminant, and any x value bigger than 2 root 10 will give a positive discriminant. So that means that, sorry, not x values, m values. So m can be less than negative 2 root 10, or m can be bigger than 2 root 10. Determining the rule for a parabola. So again, depending on the information you've got, that defines how you should start off with your equation. Even if you want to ultimately give the equation in that form, if you've got the turning point, you start with this form, you get the equation, then you expand it out to get it into that form. Okay, so don't be defined by if a question specifies the form that your answer should be in. Don't assume that means that that's how you should start. Just focus on what information have I got, what's going to be the easiest way to find the equation, then worry about getting the equation into the correct form once you've got it. So if you've got the turning point, you're going to start with turning point form. If you've got the x-intercepts, you're going to start with the factorized form because you should be able to immediately write down the brackets. And if you've just got 3 random points that are not x-intercepts or turning points, you'd start with general form. And in those cases, we'll mostly use our CAS. We'll do an example of that. And it's quite an important skill that'll come up in lots of other contexts, lots of other function types will do similar things. Okay, determine the rule for the graph pictured. So I'm looking at this graph and I'm seeing that I've got the turning point, which means I'm going to start with turning point form. So we're going to start with y equals, now we don't know about the dilation, but we do know that the graph has gone to the right by 2 and up by 3, and so we can start at this point. Students make mistakes by not considering the dilation. Students also get themselves confused by calling this negative a. Now yes, I can see from this graph that my a value is going to be negative because I've got a sad parabola. Okay, but I'm not going to write the negative in the equation. I'm just going to know that when I calculate what a is, I expect it to be a negative value, and if it isn't, I've done something wrong. I think it's too easy to get yourself confused about, putting in a negative and then you end up sort of doing double negatives where you don't mean to. Okay, but we need to find a, which is what this extra point is for. So we know when x equals 0, y equals negative 9, so let's put that into the equation. Negative 9 equals a times 0 minus 2 squared plus 3. So negative 9 equals a times negative 2 squared is 4 plus 3. Let's take away 3, so it's negative 12 equals 4a. And so a equals negative 3. So good, I'm happy because a is a negative value. And so therefore my equation is negative 3 times x minus 2 squared plus 3. Now the question doesn't specify the form of the answer. I can leave it in turning point form. There's nothing wrong with that. Okay, part B, determine the equation of the parabola that has x-intercepts at 4 and negative 1 and passes through the point 1, 6. Okay, so when we know the x-intercepts, we can start from a factorized form. So we know that if there's an x-intercept at 4, when it's factorized, the equation must have a bracket that is x minus 4, because that's how we get x equals 4 as one of the x-intercepts. And if there's another x-intercept at x equals negative 1, the bracket must have been x plus 1. We don't know about the dilation because, okay, 4 and negative 1, there's infinitely many parabolas that we can draw that have x-intercepts at 4 and negative 1. Okay, we want the one that goes through the point 1, 6. And so it's probably, I can tell from thinking about the drawing, it's probably going to be something like that. 1, 6, sorry, no, it's going to be upside down. Because it's going to be 1, 6 sort of here. Okay, but you don't need to think that through. Having drawn it, yes, a is going to be negative, but if you haven't, that's fine. You're simply subbing your point in order to find what a is. So y is 6 when x is 1 is what that point tells you. And then we can solve this. Now, some students get confused here and they try and use the, expand out the brackets. You don't need to expand out these brackets. You can work out what 1 minus 4 is, and then you just multiply. 1 minus 4 is negative 3, 1 plus 1 is 2. So it's a times negative 6, dividing by negative 6, so a is negative 1. Okay, so it's not a dilation, there's just a reflection, and so therefore the equation is negative x minus 4 times x plus 1. You can stop there, and I would advise that you do. The more work you do, the more opportunity you have to make mistakes. You might see the answer might have that negative in the bracket, might be 4 minus x times x plus 1. the whole thing might be expanded out, which would give you negative x squared plus 3x plus 4, whatever. They're all the same. They're all the equation of the line. Unless it specifies a form, any of those is fine. Determine the equation of the parabola that passes through the points -2, -6, -1, -8, and 3, 24. Okay, none of these are intercepts because there are no 0 x coordinates or y coordinates, so they're not useful, and it doesn't tell us that any of those are the turning points. We just got 3 points. In this instance, I would start with general form, okay, and I would define it using function notation, which we'll review but should be pretty familiar with by now. Because that makes it easier with our CAS and easier to write down what's happening in terms of more efficient. Not easier, but more efficient. Okay, so we're going to let f of x be the most general quadratic, ax squared plus bx plus c. And we're going to define that in our CAS. We need to be careful when we define it because it's not ax squared, it's a times x squared is what we mean, and you need to explicitly say that in your CAS. B times x plus c. Okay. Then we want to sub in the 3 points. So we know when x equals 2, y is equal to -6. So that means x equals -2. F of -2, subbing x -2 in place of x, will make the function equal -6. F of -1, subbing -1 in place of x, will make the function equal -8. F of 3, so subbing 3 in place of x, will make the function equal 24. Heaps more efficient. You don't need to actually do those substitutions yourself. We'll get our CAS to solve those 3 simultaneous equations. And we can get our CAS, we don't ever need to see the equations. So we're going to have simultaneous equations, menu 3, 7, 1. There'll be 3 equations, and the unknowns in those equations will be the coefficients, a, b, and c. My first equation, having defined the general form of the function, the first equation will be f of -2 equals -6. The second equation will be f of, so we've got that bold f, which is good, that means it's accessing my defined function, f. F of f of -1 equals -8. And f of 3 equals 24. And we find a equals 2, b equals 4, and c equals -6. Be clear about what the question's asking you. If it said, you know, a parabola has equation y equals ax squared plus bx plus c and goes through these points, find a, b, and c, then you've answered the question. A is this, b is this, c is this. But this question says determine the equation, so I actually want to write down the equation. And so therefore the equation is y equals 2x squared plus 4x minus 6. Okay. There's a screenshot there of a different example, but same process of how to do that. So define the general form, sub in the points using the function notation, and solve them simultaneously to find your unknown coefficients. This will work with cubic, all sorts of other function types. It's a process we use frequently, so something to be familiar with. And the work from the quadratics was exercise 4a and 4b. 4a is a general review of a whole lot of quadratic stuff. 4b is determining the rule of a quadratic.